Welcome everyone. Today we are going to talk about building the entities from partial messages, and that's why we call it assembling the puzzle. And I'm Can Burak. I'm a data engineer at Google Cloud PSO, and today Israel is with me, who is my colleague.
Hello, everyone.
So without further ado, I can continue with why we needed this architecture and why we needed to build these entities from pieces, because the information that we received was actually scattered into many events and many messages, and we wanted that information to be complete. The business reason behind that was the source system was thinking to optimize the network usage, and since the whole entities can become quite large for the network, they were sending only the updated portions of the data with an identifier. And during today's session, we will implement it. Israel will have a demo, and he will show us how this happens in an e-commerce website scenario. That's why we have this image with the add product to cart, checkout, etc. But think it like every click in an e-commerce website is sending an event, and that event is not complete. It is just like the user ID and just one bit of information. And also, for a complete history, we needed to create a record in the database for each event, for each click, for each update. So this was our challenge in our hand. Of course, the business side is one thing, and then the other hand, we have the technological challenges, and which is coming with the streaming data. So the messages can be late. They can arrive a couple minutes later, or maybe even a couple days later, depending on the source system, its load, its architecture, and they can arrive out of order. Depending on the message bus or message queue you are using, there can be duplicate messages, and unfortunately, there can be also some missing data. So these are all very well-known challenges in the streaming side. While we are addressing the business topic, we also need to keep those in mind, and we should build our architecture or design our architecture around these constraints. So our first approach or our first idea was to utilize the states in Apache Beam, of course, but there are three potential issues with the states. So they can easily become costly in a high traffic environment. If you keep everything in the states, then state can get large very quickly or huge very quickly, and this may increase the cost for you. The other thing is, if you are only using the state and if you are waiting for an entity to be complete before clearing it out of the state, then you may have zombie entities in the state which are never be completed, depending on the scenario. For example, if a customer puts something in their cart and leave it there for 2 years, then you will keep this uh, entity or event in your state for 2 years. So this will just pile up and it will create more and more zombies. And the final potential issue is the performance bottleneck. As your state grow in size, the search, finding the correct entities in the state can become costly, can become slower. So these are the three things also we wanted to avoid while we are building the solution. And another question was like, if the state goes huge, can it cause an out of memory issue and kill your pipeline? Israel, do you want to step in here?
Yeah, this is actually a very good question. So a question that I get often when I'm working with customers around streaming pipelines. So the short answer is no. Okay, so the short answer is no, because a state is meant to be like with the right runner, say data flow, Flink, whatever. A state is meant to be as large as necessary, but in a horizontal way. So normally when we are working in streaming, so we are always doing key value processing. So there's a certain key, for instance, a session ID, and then all the values, all the items that belong to that session. So we could have lots of sessions. So horizontally, you are never going to go to have any kind of out of memory problems, because the pipeline should scale. And if the pipeline cannot scale because, I don't know, say you don't have enough workers for the amount of work that you need to be done, so then, well, so the state will wait in the state backend until the pipeline is able to catch up and process it. The problem that you could have is with the vertical size of the state. So normally the databases that are behind the state backends are meant for data that scales up horizontally, not vertically. So you cannot put a huge amount of a state in a single variable for a single session. So there's a certain vertical limit. Normally, this vertical limit is large enough for a streaming application. No? So in a streaming application, each one of the messages should be small, for some definition of small, and that would be lots of messages. So if you fulfill this pattern, so there shouldn't be any kind of out of memory errors. But this is actually a very pertinent question, because whatever design you make, the size of your state variables should be bounded somehow. Okay, say for instance, you cannot put a list in a state and not put any kind of precautions or limits or checks to make sure that the list doesn't grow beyond a certain limit. Because if you have a list that is, I don't know, say 1 million elements, that might actually exhaust the maximum size of a single state variable. So in summary, no, it shouldn't cause any kind of out of memory errors, in particular in this case that we are dealing with here and that we're going to see in the example. But the vertical size, it matters. So make a design that makes sure that each one of the elements and the state is small enough, and if it grows, it has to be bounded. It has to have guarantees that it will not go beyond a certain size.
Thank you, Israel. So keeping in mind the business restrictions, the streaming restrictions, and the downsides or the potential pitfalls of the states, we build a solution proposal. And this solution proposal is actually consisting of two level or two-tiered states. The first one is the beam state we have. So it is the local state. So our pipeline can reach the data in sub-millisecond. And for the high velocity environment, that is great to build that entities from the pieces. And we use this only for the active data. And we had a timer. When the timer is ended or completed, the data became inactive and it is moved to the second tier, which we used Bigtable in the back in the days. But it can be anything. It can be even a file, for example, so that the data is persisted. It is cleaned from the Beam's memory, and also it makes it visible to external services. So if you want to build a reporting, for example, even with the incomplete data, you can use it. And depending on the technology you are using, you can easily scale out. And why we choose this path? Because it is cost efficient, and it also provides or increases the stability of the system. And we are avoiding the three pitfalls that I mentioned in the two slides before. I will very quickly show our basic architecture. So we had an input topic, which is pushing data into the cloud data flow, our Apache Beam pipeline. And our first level of state is the Apache Beam state. So we were writing and reading the data where we were completing it. And whenever the timer is hit, the data was moving into the cloud big table. And I will show you a state diagram in the next section, and I can tell you more. And for each event, we were pushing data into an output database. In example here, I put Cloud SQL, but you can use anything like the BigQuery, Bigtable, or any other technologies you choose, of course. And building an entity from the pieces is not a straightforward process. So this piece of art is also prepared by Israel, and it shows our flow. So when an event comes in, we were checking if there's any previous data, and this is actually first checking the, let's say, hot cache, the beam state. And if we cannot find it, then we will check the second tier of the cache. Then depending on the flow, so if it exists, we were adding or updating the fields, etc. If it doesn't exist, we were creating a new entity. And as you can see, it's a huge tree that depends on the incoming message. So we were checking if the message is newer than the data it exists, if it is a new entity, if it is an update, or if it is a late update to an already existing field. So it's a huge ball of or huge web of spider. By saying that, I will give it to Israel for the demo so he can show us this in action.
Thanks. So we're about to see an example. So the previous example shown by Jan-Burak is from a project where we worked together with a customer. It was a super fun project. You can see that in the state diagram that we had to infer out of some documentation because it was really super complex. The example that we're about to see is much simpler, okay? So we have a shopping cart and we are just adding items to the shopping cart. That's it, okay? Or also removing items. And then we need to reconstruct the latest state of the shopping cart every time with all the problems that Jan-Burak has mentioned, when sometimes we have missing data, when we get the data out of orders, and so on. So everything is in this GitHub repo already available, and well, I'm about to show you the code. So if we can switch to the code view. Okay, great. So this is the main code of the pipeline. So I'm gonna be showing some code so you get an idea of how the code looks like. And then what we're gonna be doing is running a unit test that is especially prepared to show some of the things that they want to show about these two levels of state. And we're going to be running that in debugging mode so we can see what's going on in each one of the lines. But before that, let's navigate a little bit through the code to try to understand what this pipeline is making. So this is the main function here. So we have some options, input options for the pipeline. You may be wondering whether you need here a runner to run this. This is meant to be run locally, everything locally. So you will see now that in a bit. So all the events are generated internally in the pipeline, and it's only using text files in your hard drive as external state, and the output is written in the standard output. So let's see that. So let's go here to this function here, create pipeline. I'm gonna be navigating the code. So we get here first the pipeline options. The options themselves are really not so relevant here right now. Then we get some events. The events are created in JSON format. So here we're gonna get some JSON, and we need to parse the JSON. So we do that here in this line here. Because the parsing may fail, so we are returning here two collections in a tuple, okay? So the good parsed messages and the bad messages that couldn't be parsed, okay? With the bad messages that couldn't be parsed, we don't do anything in this example, okay? So, but just let's say, in case you were wondering why we are returning here a P collection tuple, it's because of that. Very typical pattern in any pipeline that is doing some parsing, right? Then this is very important. In streaming, in order to use a state, you need to have key values. Here we have key values of strings and events, okay? So this event, let me go quickly here to show you. So this is just a data class with some data here, a session ID, a timestamp, event type, and so on, okay? These are items that are added to a shopping cart. And the string here is the session ID. All the items that belong to the same shopping cart, they have the same session ID. Okay, so, and if you are a user and you return, let's say, in a few hours, and you create a new shopping cart, then that will be a new session ID. So here we are just adding the key, and then we have the data all ready to be using a state. Okay, so remember, anything that you put into a DoFn that is using a state needs to be key values. This is in Java. You are seeing here the example in Java. If you do this in Python, for instance, so key values are just tuples with two elements. The first element is the key. Second element is the value, right? And then we take these events and we do here all the algorithm to recover the sessions doing the merge. So this is where all the logic is. And this is where I'm going to focus in a bit. I'm going to continue with the pipeline so you see the full end-to-end pipeline. But this is where, let's say, the core, the important part of this pipeline is. You will see a lot of code in the repo because you need to do a lot of stuff. Okay, so you need to parse, you need to generate the events and so on. But this is really the crucial part that is probably relevant for you. So you can, let's say, almost ignore the rest and focus here if you want to see how this logic is implemented. Sometimes, because of the lack of consistency in the data, we may not complete an order, okay? Say that we have so much missing data that it's impossible for us to reconstruct an order. In those cases, so we will return some failures here, okay? But when we are able to recover the order, even if the messages are out of order, they are shuffled, so we will produce an order, and then, well, so the failures are written to the standard log error, okay? So they are here like written as error logs. The rest of messages are just written to the standard out. So you don't need anything to run this pipeline, just your computer. In this case, you need a Java development kit, and you can run this, okay? So you have all the details in the repo. So about that. So you can run this locally. No need to do cloud or anything like that. Okay, so let's go and focus here in this function, here in the merge function. So this is a P transform that takes as input this, okay, and then it returns as output the P collection tuple. Remember, the good things are orders, the bad things are, well, just a string with some message because for whatever reason we couldn't reconstruct the session. Inside this transform, so we have also here a merge DoFn. Okay, so there's a lot of code. Not all of the code is so important for the explanation. This DoFn is the one that is doing the key value state processing. Okay, you can see here that this will get this as inputs. Okay, and it will be returning every single time an order. Okay, so every time it sees a message, it returns an order. That is a partial order, probably. When a new message arrives, it tries to reorder the messages and recover the order. All this logic is in two methods in the DoFn. Okay, so it's in the process element method and the on timer method. Okay, so in the process element method, I'm gonna put here a breakpoint. So I don't know if you have done debugging of Apache Beam pipelines sometimes. Okay, so I have seen sometimes people putting, I don't know, a breakpoint here. Like for instance, in this part that is doing a P collection. There are two worlds inside a runner of Apache Beam pipelines. That is the pipeline construction moment and the pipeline execution moment. The pipeline construction moment, it doesn't make sense to debug that. So it doesn't make sense to put a breakpoint here in this point because this is still constructing the pipeline. So you need to go inside the process element methods of the DoFns or inside the methods that are actually receiving some data and doing something with the data. In a DoFn, this is the process element method. In other places, like a combiner, it could be other methods. Or it could be also other methods, like, for instance, the timer methods here, okay? So I'm going to put two breakpoints here, this here, so it will stop when it starts processing data in the process element method, and later when we start running the pipeline, we will actually go through the logic. Not now, so I have been talking too much. Let's move to some action in a bit, and I'm gonna put another here, another breakpoint here, because as Jan Burak said, the way this pipeline is going to work is it's going to be using internal state to try to remember what has happened in the past and to be able to reconstruct the order every time there's a new message. Remembering the past is crucial to be able to reconstruct the order, even if we're seeing the messages shuffle, let's say, in a different order to the one that they were produced. But we cannot keep things in the internal state forever, especially for very large scale pipelines, because that can be easily become expensive, or you can have performance issues and so on. So we have this timer, as Jan Burak explained, that every once in a while, it will take the internal state of the pipeline and it will freeze it in this cold storage, which is files in our case, and then it will wipe out the internal state. And then if for whatever reason, after this timer, we see a new message belonging to the same session, we will go to the cold storage and we will recover the state, and then we will warm the internal state. We will write again to the internal state to continue processing in the internal state. This pattern allows you to improve performance when you have very large state and you have periods of times when maybe you will not see data about one session, but it has also other, let's say, very nice side effects. For instance, how do you observe the internal state of your pipeline? Like say you are using Dataflow. The internal state, there's no place where you can go and make a query and grab all the state of your pipeline. And if, for instance, you drain your pipeline, all the state will be lost. So if you run a Dataflow pipeline with this pattern that is written here, so you will see actually when it drains, it will write all the state to the output, because the timer will be fired out, will be triggered, and you will see that state in your output database. In this case, it's just files, but you will see that in your output database. Okay, so I promise I'm going to shut up, and then we're going to see the action. So here there are a few unit tests in this project. Let me put a little bit here more of a space because I need the buttons here. Okay, so there are lots of tests, 44 tests. Okay, because well, in the times of coding agents, writing unit tests is fun again. Okay, so it's not painful anymore. But the one that we're going to be seeing here is only this one here. So this is the demo test. This one is going to generate some data, and it's going to showcase this offloading to the external storage. So I'm going to press here debugging, and hopefully it's going to work. So we're going to see that in a second. It's compiling. Okay. It will stop. It should stop. Okay, great. It has a stop in the first element of my processing. Okay. So we don't see here still the event, okay, the element, because we have a stop here right in this line. So I'm going to get this down, and we're going to go line by line, okay? So we see here, this is the first session, session 1, okay? And then the event, okay? Well, something here. The contents are not so relevant, okay? So we have got the first event. Now we're going to read the internal state. Will we have something in the internal state at this point? No, because it's the first time we have seen a message. So we can see that order is null. This is fine. This is the first time we are processing. We have to start somewhere, right? Now we're going to look up in the external state because we don't have anything in the internal state. Maybe is it because this is a very old message that arrived out of order and we need to go to the external state to recover the session? Well, it is not the case here because, again, as I said, this is the beginning. And because this is the beginning, we create a new order, okay? And then we add the event and we write it to the internal state. And then we set the timer, we emit the output. Okay, I don't care. I'm going to move on to the next message. Nice. I have moved on to the next message. So it's stop again in the next item. We can see that the session is the same one. So these are two messages that are sharing the same key. So they are also sharing the same state variables. State variables are bounded per key. Different keys will have different state variables. These are the same key, so that should be something in the state. Now, this should return something, okay? Because, well, we just wrote it in the previous message, right? So let's press C here. Okay, good, good. There's something in the order. You can see this here, that we have recovered the previous order, that it had only one event in the order, okay? So let's move on. Is order null? It is not null, okay? So because we have already this order in the internal state, so let's add the new event, okay? So here you see that I size 2 now. Let's write the state again. And I'm gonna move on to the next message, okay? So the rest is not relevant. Hey, wait, what has happened? if you look at the unit test, you will see that we are controlling the watermark. So now we have put the watermark in a way that has made the trigger, the timer trigger at this point, okay? So these messages are already old, okay? So by the definition of old that we're using for the unit test. So what is going to happen? Well, we're gonna take the order from the internal state. Here it is, see, it's size 2, the one that we just wrote, and we are gonna write it into the external state, okay? So to write it to the external state, so we need to use this function here. And because I don't know exactly where this is going to be written to, I'm gonna enter into this code, okay? So, okay, sorry, this one here, no, this is not where I wanted to enter, okay? Let me see now. This is not either where okay, I made a mistake here, let me, okay. Now, this is the one where I wanted to enter, okay? So let's see where this is written to, okay? Okay, here's a path, okay, let's move on. And now let me see in the debug console where is this path, okay? Let me put here path. So we see here this, okay? Good. So let me go to the terminal. It's JUnit 1613. Let me recover it, okay? So PMP, the unit 1613. So you see here that there's a directory state. So this pipeline is done in a way that is writing to the external output, okay? So we go here, state, and there is nothing. It's empty. Okay, good. It doesn't matter. Let me go back to the code. Let me go back here to the code. Let me run this. Okay, this is already written to the external state. Let's see this. See, now there's a file here. Let's have a look at its content. Well, not surprised. This is the file. This is the same order we just saw in the previous. Well, it's not well formatted for some reason, but this is the data that we have seen. Okay, great. Okay, so let's move on to the next message now. Now we have yet another message now here. We move to the next line, demo session 1. So this is the same session. This is the event. What is going to happen now? Because we have written to the external state, the state internally is now empty. See, order is null. Okay, no big deal. This is what we want. This is what we actually wrote the code for. Now the order is null. Let's have a look at the external state. Now it's going to go to this file that I told you, and it's gonna recover the order. And you see, you have here now the order with size 2, okay? And then we are gonna continue. We're gonna write it to the internal state to warm it up, okay? Because, well, we have seen a new message for session 1. So maybe we will see messages coming also, because I don't know, that will be another sequence of messages coming for whatever reason. So let's load this into the internal state and keep it for a while here in order to be able to respond faster to these new messages. It's always this trade-off between having very low latency internal state, but not also populating the state with all my data waiting forever. Because I need to for performance reasons, for cost reasons, I need to keep it bounded somehow. Okay. So then, well, we order a new one, we write it again, and then we continue. I'm gonna continue. Okay. Another timer fire up. Okay. So then this is gonna write the output to the external state. And with this, well, it's already finished, okay? So you have seen this in action. So what it has happened, every time we got a new message, we put it in the internal state, we put this order class in the internal state. The size of this class is not bounded. You could have 1 million items in a shopping cart, maybe, okay? But because of the kind of data that we're handling, it's very unlikely that you will have something like that. And then every once in a while, we were offloading to files in the hard drive as an external storage in order to save space in the internal state. Go to the repo and play with this test here. Okay, let me show you here. This one that I'll say Beam College demo test. There are a few others to try to showcase all the other scenarios. Remember where to put the breakpoints in order to be able to do the debugging in the right way. And have fun. So let's see if you can apply this to your pipelines in the future. I think with this we can move on now back to the slides. Okay, so everyone, so thanks a lot for your attention. So please grab the repo in GitHub